and welcome everybody. For many, it's the afternoon, so wish you a very nice afternoon. The previous talk was interesting in the sense that the material is and the application is important to the choice of lasers. This is a little bit the approach of Laserline as well. Use the appropriate tool for each application individually. I'll be looking at a quick introduction just on the company Laserline for those that don't know, the main products and applications that we see in general for our lasers. We'll be looking at the process of cladding, the main and established cladding applications, and then go into detail of the ELA process, extreme high-speed laser cladding process, that we use as basis. It's the introduction also into the cladding of brake discs, maybe the main focus of my talk in the following. A very nice, very interesting, and very promising application for diode laser cladding. We'll then look into some of the further trends in cladding, as mentioned here, before going into the summary of my talk. So let's quickly look at the company. The company is 23 years old now. It's privately owned and managed company. There's something like around about 300 people in the headquarters in Mülheim-Kärlich, just outside Koblenz. We are halfway between Frankfurt and Cologne, easy to access by plane to Frankfurt or Bonn-Cologne. The company is present globally. We have subsidiaries and distributors all over the world, so we are able to serve our customers everywhere in the world. We are considered as market and technology leader for high-power diode lasers. We are really concentrating on diode lasers and some special lasers coming out from such diode lasers as a special version of fiber lasers. We call them converted diode lasers. We also now have blue diode lasers that were presented in the webinar number 1 2 weeks ago, roughly. We also provide beam delivery fibers, optics, accessories together with the lasers, but we don't build machines. And you will see from the ongoing presentation that we are deep into process know-how, process development. So we have currently 4 big, well-equipped applications labs where we do process development, where we help people see feasibility, see how things work out. And this is where most of the developments I will show to you in the following have been made. Let's look at the main applications. I'm sorry for the wrong photo in the first slide. This should be a cladding and not a welding slide. We'll go into more detail of the cladding, which is a historical, very well-established application for diode lasers. When I started at Laserline in 2001, we had the first industrial applications with one of our customers in France that has evolved to something like 40 installations worldwide just from this one customer. And it's still one of the most important applications for our lasers. So this is what we'll be concentrating on in the following. Very nice application for diode lasers is also with heat treatment, shown in the second photo from the left, which is mostly hardening applications. There's also some softening, but also applications where you simply need a very large homogeneous spot that heats, softens, dries, or just irradiates the surface of workpiece. Joining applications traditionally come from heat conduction welding because diode lasers are difficult to focus to a small spot, so they're not used for cutting or engraving, for example. Joining applications so started with medium power and large spot for heat conduction welding. They are very well established in automotive industry on brazing applications, and in the last at least 5 years plus have been established in keyhole welding. for example, in tailored blanks welding for automotive parts. There's a range of other applications related to plastics treatment, for example, tape placement of carbon fiber reinforced tapes, as you can see in the picture on the very right side. This is carbon fiber reinforced plastics that is molten using the laser and is used to build. This is the start of a container for hydrogen, hydrogen cars, for example. You can see in the picture here. Going right into the subject of established cladding applications, a quick overview of the procedure. How does this work? The principle in this case is that the laser beam shown in the right top picture heats the material, surface of the material, powder or wire is fed into the laser beam and into the molten material is molten into the surface. This way you get a molten track on top of the material, and then you can, as you can see in the lower right picture, either put tracks next to each other or eventually on top of each other to achieve 3D printing or additive manufacturing, so which is very closely related. As opposed to conventional welding with TIG or PTA, you get very low dilution with the substrate, so you can have very thin layers only, as opposed to flame spray or plasma spray cladding. You get an excellent mechanical bonding that is normally metallurgical bonding. At the same time, you get high density, so that's very nice for 3D printing. You get a very high density. The overall process is very time and material efficient. So the main process, and we're putting this at Laserline in these 4 categories, is remanufacturing or repair welding. We'll see slides on this in the following. The traditional and oldest application is wear and corrosion protection. We'll also have some slides on this. There is 3D printing when you put layers on top of each other. Also in hybrid machines. And there's some special applications where you want special features in the surface. For example, when you try to get some signal information through a tube, then you want to have special materials in the surface that avoid interference for a sort of measurement. Typical example, quite recent example, is corrosion protection of boiler tubes, as you can see in the 4 pictures here, just different views of such boiler tubes as examples of applications for corrosion protection. This is from oil and gas industry. On the lower right corner, for example, you can see one of the stabilizers that stabilizes the drilling tool in the main oil string that goes down deep for oil drilling and stabilizes this oil string towards the sides. And so this is tungsten carbide clad into the surface for wear protection. Tungsten carbide in typically nickel bases or nickel alloy bases. I mentioned the examples of repair welding, also very well established. This is from a Spanish customer. You can see on the upper left corner, you can see the worn out shaft from some rotor for petrochemical industry. On the lower left side, you can see the clad surface. On the upper right corner, you see the process. And on the lower right corner, you can see the finished part as it is, comes out from the machine after machining of the surface. In many cases, the repaired part is better than the original part because you can use more suitable, maybe more wear-resistant powders in the process. The last, also very well-established process is 3D printing, additive manufacturing, maybe the most recent one of the established applications. This shows an example of a part that is something like 20 centimeters high and was built up in less than 50 minutes. There's a very high powder deposition efficiency, so more than 80% of the powder is in the final part. So this is a demo part in the shape of a blade, also with very low porosity and built up really from the simple plate you can see from the beginning. Let's look at the high-speed cladding processes like ELA and others in the following that I will then need for the brake disc application. The principle was invented and patented also by Fraunhofer ILT in Aachen. A lot of the process development was done with laser line lasers, and the main principle, as opposed to conventional laser material deposition, LMD, or laser metal deposition, is that a lot of the laser power goes into base material, and the powder blown into the molten layer is then molten together with the material, as opposed to the ELA process, more with using special nozzles, adapted nozzles and a slightly different offset, also much smaller laser power, typically smaller laser power and smaller laser spot. You would deposit more of the energy into the powder itself and less into the substrate. As a result, you get thinner layers, you get less dilution of the base material, so you can work with thin and very precise layers. This is one example, calculation example of a hydraulic plunger, and you can see from the graph here, taking so typically you would have much quicker movement of the part. So typically the process is applied on parts that are symmetric, rotationally symmetric, so you can rotate them at a high rate. You have a much higher deposition rate, in particular in area, and at the same time you work at thin layers, which is sufficient for this process. Looking at some of the results, so I mentioned very high surface rate, quite high feed rate, that's why you need symmetric components. Typically, as with all laser cladding processes, you will get a fully metallurgical bond, and you can have very thin layers. And because the dilution is so thin, so low, you can use thin layers where you have the full quality of the added powder. The process in the end becomes very efficient, simply because you can work with lower power, you can work with less powder because you have thin layers, so it's environmentally and also cost-wise very efficient process. And this is the process that we use for the cladding of brake discs. Why would we want to clad brake discs? Quick introduction into the subject. The European Union is currently planning, as other countries as well, maybe this comes in 2024, to ban conventional brake discs that are simply built from cast iron, typically gray cast iron, that produce a lot of fine dust, particulate matter. In fact, according to some of the figures, 1/4 of the fine dust, or more than 20% of the fine dust, depending on which fraction of particle size you look at, comes from the brakes only. Still, the most important part comes from the exhaust, but this portion also needs to be reduced. And one way of reducing the fine dust that is produced from brake discs that are not clad or treated in some way is what we are trying to address. There's already a solution that exists. To my knowledge, it's used for the Porsche Panamera only. That's the iDisc from Bosch and Buderus. It's a thermal spray layer, and as I mentioned before, this is simple mechanical bonding, and also requires quite a lot of powder. So it's a less efficient process than what we are trying to find with the laser process. Let's look at the laser process. We need two layers. We need a buffer layer consisting of typically the surrounding metal base where the chromium is placed in for the top layer. So you have a purely metallurgical layer as first, quite thin layer, and on top of this a carbide containing layer that takes care of the wear resistance. Why do you need the buffer laser layer? The reason is that the carbide layer has tendency to cracks, and then you would get a corrosion problem through the cracks of the carbide layer. This is why you need several layers, and we've done this development together with a car manufacturer and manufacturer of brake discs. And the aim of this project, so this is on standard brake discs for passenger cars in the diameter 300, 350 millimeter. The idea is to get 100,000 of such brake discs per year and per machine. And some simple calculations show then, because we have to clad the brake disc from both sides with at least two layers each side, that we have something like 2 to 3 minutes cladding time for each side, because in the following, the brake disc is also machined, grinded to remove the rough surface and get a nice shiny surface in the following. So the development we did was aiming at 2 to 3 minutes per side, which requires quite a lot of laser power. So the development we did in our Laserline lab in Koblenz was based on laser power between 8 and 22 kilowatt. To move on a little quicker, some of the results we can show here. So we've seen, as requested, very low dilution. It's down to 1%. And the main reason for this is that the diode laser produces a nice top hat beam profile. You can see from the micrograph on the lower side, the lamellar graphite with directly with the clad layer on top. In this case, there's no buffer layer. What is interesting, what's important, there's no cracks, no pores, and we get a very nice metallurgical bonding. So in the end, Laserline is able to show a complete brake disc cladding solution. We've shown the process. We're able to produce on one machine 100,000 parts per year and lasers. And all of these solutions were developed with Laserline diode lasers. We can now reach up to 45 kilowatt. The processes we did for this case were between typically 8 kilowatt and just above 22 kilowatt output power. Let's just look quickly at the last slide's further trends. So that was on the brake discs applications. We can see more and more applications looking at wire-based cladding. So we are also able at much higher efficiency to add wire into the surface of a material, in particular for 3D printing as an example. We see the trend, you've already seen this from the brake disc application, the trend in cladding moves more and more towards very high power. So we've been able to show extremely high deposition rate. In this case, it says 35 kilogram per hour deposition of cladding powder using 50 kilowatt output power. So we see the trend in this direction. What is also interesting, a new laser based on blue diodes. In this case, it's a hybrid process, infrared and blue diode laser using as a combined process for cladding of copper powder onto a copper substrate, something that would not work with another wavelength simply because of the problem of absorption. Quick summary. I've introduced the company. We see ourselves as market technology leader for high power diode lasers. We provide lasers, beam delivery, and processing optics. We have extensive application know-how. We can support customers in the application. I've shown some of the established cladding applications, in particular for wear and corrosion protection, but also for 3D printing. We've looked at the high-speed cladding of very thin layers with low dilution. Based on this, we've seen the cladding of brake discs with the aim of reducing fine particles in the range of 8 to 20 kilowatt power. And we've had a quick look at further interesting applications, wire-based cladding, very high power cladding, and cladding with blue diode lasers. So thank you for watching. Thank you for listening. Please use the question and answers session with your specific questions. Don't hesitate to contact Laserline via email. We can do Zoom conferences. You can call us by telephone and have a look at our internet page, because there you'll find a lot more information, more than was possible in the few minutes I had now. Thank you for watching.